activation function. Until now, we already discussed about some of the activation functions. What is the first activation function that we discussed? G of x equal to e power x by 1 plus e power x. This is used for classification. What is the name of this activation function? What is the name of this activation function?
Linear.
Hmm? Is it linear?
It's logic. No,
It's for classification, right? It's what is this called? Sigmoid, isn't it?
Sigmoid.
Logistic function or sigmoid function. What is the linear activation? G of x equal to x, that is linear activation. Okay, these are what we have used until now. What are activation functions? In simple words, h1 is a function of x1 x2. Like yesterday, very detailed manner we discussed, isn't it? H1 is a logistic regression. We took a classification example. H1 is a logistic regression, G of x. H2 is G of x. Though we don't show it, but internally we imagine that. Yes or no? All of you comfortably imagine h1 is a function of x1 and x2. Yes or no? Your y is also a function of h1 and h2. We do not specifically put g of x here, but we know that w naught, w1 x1, w2 x2, or w naught, uppercase w naught, w1 h1, w2 h2, apply sigmoid g of x on top of it, you will get the target value y. So this is what we discussed, right? Yesterday, right? Now, if it is linear, if the output is not classification, it is not 0 and 1. If it is linear, if it is a kind of regression approach, then what will be g of x? Until now, g of x is e power x by 1 plus e power x. For linear case, what will be the g of x? It will be g of x equal to x. For classification, we use sigmoid function. I think we know the story of sigmoid function or the logistic function, e power x by 1 plus e power x. Okay. Sigmoid, it can be written as 1 by 1 plus e power minus x. Both are one and the same. It looks like an S curve. Now, there is a different function which looks like this. First of all, why did we even choose sigmoid for classification? You remember the story behind sigmoid? You remember the story behind the logistic function? We chose this because it looks like an S curve and our data is like this. It is perfect for us when the data is, our data is either zeros. Do you remember that story? When the data is either zeros or ones, if you build a straight line that doesn't work, you have zeros and ones, then we will take a function e power x by 1 plus e power x logistic function that will work for this. There is another function that also looks like an S curve. Do you know that? There is another function that looks exactly like an S curve. Similar to this. However, sigmoid is between 0 and 1. That function is between -1 to +1. Don't worry about it. I don't care whether it is between 0 and 1 or -1 to +1. There is another function which looks like an S curve. That is known as tan h function. What is it? Tan hyperbolic, tan h. Tan h is sin h by cos h. I think this formula everyone knows. But the exact formula for tan h is e power x minus e power minus x divided by e power x plus e power minus x. This also looks like an S curve that is between -1 to +1. Mathematically, this, somehow this tan h internally it is converging much faster for the same problem statement. Same problem statement. If you are already solving it within 10 seconds, I cannot really show you a lot of improvement in the time. However, if a problem statement takes 100 seconds using sigmoid, if you use tan h, it will take maybe 50 seconds only. Or if it takes 100 epochs in sigmoid, it will take 50 epochs in tan h. Why? Because of the function, because of the derivatives internally, somehow mathematically, it is much faster. Tan h is converging much faster. So when is this option used? All of you make a note of it. When is this tan h option used? Tan h option is used when you want to reduce the execution time. Sometimes execution time is very important for you, especially if your algorithm is taking more than 1 hour time, especially if you're more than 60 minutes is the execution time, you start thinking about it. Don't you think so? All of you think about it. When we have an algorithm that is taking more than 1 hour, we try to reduce the execution time as well, or we tell ourselves anyway we are getting accuracy, it's okay. Do we think that way, or we want to reduce the execution time, especially when we are building the model, when we are experimenting, we want to quickly get the results. Obviously we want to reduce the execution time. At that time, simply in place of sigmoid, if you give tanh, surprisingly it will be much faster. Let me give you a demo of this. Let us go back to our playground, all of you. We will compare sigmoid and tanh on the playground. First of all, get rid of these hidden layers. Keep only one hidden layer, get rid of these neurons as well. Okay, only two. Just get rid of all this. Take the third data set. Let me start like get rid of all this, all of you, get rid of everything. Yes, get rid of everything. Keep only this one. Even these also you have to get rid of them. Then follow me. Left side, the dataset name is third one. What is the third dataset name? Confirm it to me. What is your third dataset name? Gaussian data. Okay, Gaussian data. Ratio of training to test, you keep it 60%. Maybe keep the noise a slightly lower value, maybe at 10 or 5. Let's maybe keep the noise at 5 only. That means I want a perfect clarification, perfect data set. So I'm simulating a data set with only noise 5. Are you with me, all of you? Third data set, training to test is 60%, noise is 5, batch size 10. Batch size parameter we'll discuss later. As of now, leave it as it is. All right. X1 and X2 variables, one hidden layer with two hidden nodes. Learning rate, leave it as it is. Learning rate parameter we haven't discussed. We will leave it as it is. No regularization required. Regularization is not required. All right. No regularization. Activation. Right now, activation is tanh. Select this activation as sigmoid. There is one more activation called ReLU that we will discuss later. As of now, select the activation as sigmoid. Okay. Are you with me, all of you? Are we missing anything? Everything is set. What I want you to do right now is, we will start the execution, wait until we reach almost 0.00 error. Wait until we reach almost 0.00 error, and you're going to tell me how many epochs sigmoid takes, how many epochs tanh takes to reach almost 0.005 or 0.004, that much of error. Look at this. Ready? Start this. 0.003, 0.002 error. Let me stop it here. I got 0.001 error. Okay, perfect. I got 0.001 error on the training. The test 0.002. It took me 225 epochs. What is the expectation if I do tanh? What is the expectation to reach the same error? How many epochs tanh takes? Mathematically, since it is convenient, it converges faster. Maybe instead of 200, it will take done 50. Check that out. Let me regenerate again. Let me try sigmoid to reach 0.001. Stop it. 211. Check that out again, all of you. 0.001. Again, if I try tanh, can you make a guess how many epochs that it will take? How many epochs? Done. Can you observe the difference, all of you? Usually, if the execution time itself is very less, you can use either sigmoid or tanh. Not a problem. But this is practically when you have a problem statement which is taking more than 1 hour or more than 2 hours. Then go for tanh. Both of them are similar. We haven't discussed tanh until now, but because we never felt the need of it. In future, if you have a situation where your algorithm is taking much more time for execution, then you may have to try tan h instead of sigmoid. 0.001 error. How much time sigmoid takes? 178. This is the third demo that I'm giving. Tan h takes, done. Okay, that's it. If you are not able to see this, regenerate, select sigmoid, take a note of it. Can some of you give me your results? How many epochs does sigmoid take to reach to 0.001 against tan h? How many epoch does it take? Give me some examples from your execution. What are your results? Put that in the chat window. So somebody took 202 in sigmoid to reach the same accuracy error level. Tan h took 80, less than half. Yeah. Now we need to understand that both sigmoid and tan h, they look like S curve. Yes or no? Now when the value is really high or when the value is really low, that means when the sigmoid is near to 1 or sigmoid value is near to 0, at both the places their derivative is near to 0. The derivative of sigmoid, you know derivative, what is the derivative of x square? What is the derivative value of x square? 2x. Like that, sigmoid function e power x by 1 plus e power x value, there will be a derivative as well for it. The derivative of sigmoid is near to 0 when sigmoid is near to 1 as well as sigmoid is near to 0. Same thing goes with tan h. Due to this issue, what happens is when the network is really deep in nature, when the network is really deep in nature, how do we do in this back propagation algorithm? We do feed forward and we do feed forward until the last layer. We calculate the error. Then we do the back propagation. Yes or no? If you have one layer, you do the back propagation until here. From there, you have to do the back propagation error contribution here. You will get error contribution at this hidden layer. From there, you will get error contribution at this hidden layer, 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 this hidden layer. Then finally, after you get the error contributions here, what is the next step? Feed forward followed by error calculation followed by back propagation. What is the next step? I told you, you have to remember this song. Feed forward followed by error calculation followed by back propagation followed by weight updating. You will update the weights. Which direction you will move the weights? You will move the weights in that direction where this error will be reduced. Will you worry about the overall error? When you're making the weight adjustment, you look at only this error. When you're making these adjustments, you look at only this error. Tell me, what are we? Are we updating the weights based on the local error contribution or we are looking at the overall error? Tell me, what are we doing? When we are adjusting these weights, shall I look at the overall error or only error corresponding to this hidden node? Local error, right? Now, the issue here is if the values of the derivative, multi-dimensional derivative is something like gradient, it is known as. Gradient means your multi-dimensional derivative or partial derivative. If that value is slightly lesser, very lesser here, and a portion of that, again a partial derivative of that is much more lesser here, much lesser here, the gradient value or the derivative value, whenever you hear this term gradient, maybe for a simplicity sake you can understand that as derivative value. For minimizing and maximizing, we have to find the derivative, right? Remember, y equal to f of x. How do you find the minimum value of this? We used to do dy by dx equal to 0, d square y by dx square less than equal to 0 or greater than equal to 0. Like that we used to do all that math, right? So here in multi-dimensional case, it is known as gradient. If the gradient is less here, if the network is deep, if the value of sigmoid is really high or really low, or tan h is really high or really low, the derivatives or the gradients will be less, very less, much lesser, 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 lesser. Almost by the time you come here, almost the gradient will vanish or it will become zero, zero gradient. That means the error contribution here will be almost zero. What will happen if the error contribution by this hidden node is zero, this one is zero, this one is zero, this one is zero? Then what will happen? What is the next impact? The weights will almost remain the same, thinking in the right direction. Yes, if there is not much error there, why should I move the weights? The weights will almost remain the same. Even after the first epoch, the weights over here are almost same. If the weights are here are almost same, then what will happen? What does that result into? If the gradients or the error contributions are almost zero near the input layer, the weights will almost remain the same. You started with random weights. That means, is there any improvement after epoch 1? Is there any improvement after epoch 1? Is there any improvement after epoch to epoch after epoch, epoch after epoch? There will be no improvement because weights are hardly changing. If the input layer to first hidden layer weights itself are not changing, what will you learn over a period of time? Nothing will be learned. This particular problem is a very common problem. This is particularly a common problem in deep neural networks. If you have 3 hidden layers, 4 hidden layers, 5 hidden layers, it's fine. They are not that much deep. Especially when you have more than 10 hidden layers. Note this down. Practically, when you are working on some problems, when you have more than 10 hidden layers, it is not proved anywhere, but practically you will observe that more than 10 hidden layers, you will fall into the problem of vanishing gradients issue. What is vanishing gradients issue? Near the output layer, the gradients will be very less, or the partial derivatives will be very less. Then by the time you reach the hidden layer that is close to input layer, the gradients will almost vanish. That means error contributions in the back propagation almost get to zero. If that is the case, then weights will hardly get updated. Then nothing will be learnt no matter how many epochs we do. If the gradients values are already low, then with the multiplication of fractional values, there will be almost smaller, very, very smaller gradients. Definitely, there will be nothing that will be learned over a period of time. This particular issue is known as vanishing gradient. Vanishing gradient issue is happening because of the property of our sigmoid, where its gradient value or the derivative value is very small at higher and lower value. Somehow we need to keep this gradient alive. We need to come up with a new activation function that will keep this gradient alive. Keeping gradient alive means what? Here there has to be higher value. Gradient should not vanish. It should not get to zero. There is a new function that has been created, activation function, that will resolve this problem of vanishing gradients beautifully. That particular activation function is known as rectified linear unit function. Rectified linear unit. Rectified linear unit function is simply, this activation function is simply max value of 0 comma x. If the value of x is less than 0, it will be 0. If the value of x is greater than or equal to 0, then it will be x. What will be the derivative of x? Can somebody tell me what is the derivative of x? Do you remember the derivative of x? Easy question, right? What is the derivative of x? What is the derivative of x? 1. Derivative of x is simply 1. That means it is static. So originally this particular ReLU, which is known as rectified linear unit, it is known as ReLU, rectified linear unit. Where is it used? Where is it used? It is given as a solution for vanishing gradients issue. Where is it used? It is used in really deep neural network. How do you define a really deep neural network? Maybe more than 10 hidden layers, deep neural network. Now, what is the speciality of this rectified linear unit? Its derivative is static, 1. That means the value of ReLU is, if it is less than 0, if the input value is less than 0, it will be 0. If the input value is positive, then it will be same value. This is kind of linear unit, but it is not completely linear. Rectified linear, that is what this It is either 0 or x. The speciality of this is derivative is when it is less than 0, it will be anyway 0. But when it is positive, value of x, like derivative of 0 is how much? 0. Derivative of x is 1. So look at this. Until here, derivative is 0. From there, derivative is static. This way, the derivatives won't vanish. The gradients values will never get less than 1. It will keep alive. By doing so, we can avoid that issue of vanishing gradients. You may not face these vanishing gradient issues if you are dealing with deep neural networks that are less than 10 no 10 layers, 10 hidden layers, but you will definitely face it. No doubt about it. You will definitely face it if you are using either sigmoid or Tanh activation. You will definitely face these vanishing gradient issues. There you have to use rectified linear unit ReLU activation function. Later on, we are going to discuss something called convolution neural networks. They are by default very deep in nature. A simple convolution neural network will, like you, it will have simply 10 layers for sure. By default, they are deep in nature. No doubt about it. Definitely, they will have at least there will be always 9 layers for sure. Maybe if the data is slightly large or slightly complex, then it may have 20 or maybe at least 15 layers it will have. By default, they are all very deep in nature. By default in CNN and all that, which we are going to discuss later on, there you will be using ReLU only. By default, ReLU, that's it. But for other networks that we have built until now, we never felt the need of it. Maybe in future you may require it. We will use it when we are doing with CNN. All right. So ReLU resolves the issue of vanishing gradients. Have you understood what is vanishing gradients issue? What is vanishing gradient issue? If the derivatives are lesser here. So let us not talk in terms of derivatives. If the error contributions are less here already, by the time you calculate all these error contributions mathematically using those formulas, by the time you reach here, almost error contribution becomes almost zero. That is the point that you have to capture. That is vanishing gradients issue. And there is a function that has been introduced. I have kind of oversimplified this whole topic. This is like mathematically it has proved like what is the issue of vanishing gradients and how this actually solves and all that. That theoretical proof, we don't need to look into that once we understand this whole ReLU function. Okay. Okay, there is one more activation function left. We have discussed until now, what have we discussed? We have discussed g of x equal to x, which is linear. Okay. We also discussed g of x equal to e power x by 1 plus e power x, which is sigmoid. We also discussed g of x equal to e power x minus e power minus x divided by e power x plus e power minus x. This is tan h. We also discussed g of x equal to either 0 when x is 0 less than 0, x when x is greater than or equal to 0. This is known as rectified linear unit. What is the other function that we have, which we already discussed already? It is a very special function. It is not in between. Right at the output layer, that activation function is used. What is that function? The other function that we have discussed until now is it is used only at the output layer. It is known as soft max. I don't think I need to tell you what is it all about. Soft max, let us suppose if you have 4 output nodes, for every value you will get 4 vector, a vector of 4 values as the output. That means if you give one image or one input, you will get result from here, here and here. However, we want to take the maximum value out of this. Originally we will get only this one, this one, this one and this one as the output. Originally we get only this one as the output. In softmax, we will take the summation of all that, divide it, so that summation of all that will become near to 1, and usually we'll take the maximum out of it. What usually, as a rule, we have to take the maximum. That is known as softmax. We don't use this anywhere else. This is used in which case? It is used in which case? It is used for multi-class classification only. Yes or no? For multi-class classification, we use softmax at which layer? By the way, which layer? At output layer. Final output layer. That's correct. Okay. And how do we give this? We already have seen like activation equal to sigmoid activation. Like we don't really give like this. Just for the sake of syntax introduction, I'm giving like this. But usually we don't bit of sigmoid, relu, tan, relu. These things we will not do it. So we give activation equal to sigmoid. You can give the name, just the name, relu, tan, relu, softmax. We already use sigmoid and softmax. Okay. Similarly, if you change the values to tan and relu, you will get these values. Okay. These are some of the activation functions. All right.